Section 3.3 continued. We got as far as problem 5. Let's do a quick recap of what we had done up to this point. We were trying to set up our differentiation rules. We started off with problem 1, which was the derivative of a constant function. We were expecting the answer 0 because y equals 7 in this case is a horizontal line, and the slope of that is going to be 0. We then went on to find the derivative of x, and again we expected an answer that we got of 1 because that's a straight line with a slope of 1. That was problem 2. Problem 3, we wanted the derivative of x squared. That was a homework problem, and recall that the derivative of x squared was 2x. Problem 4, that was a starburst problem, x cubed, and the derivative of that was 3x squared. We were about to do problem 5, so let's get going on that. We're going to start with f of x being x to the 4th, and we want to find f prime of x, and we know f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. A result that's presumably completely hardwired into your brains now. So let's see, what is my function? It has an output value of whatever the input was to the 4th power. So if I have an input of x to the x plus h, it has an output of x plus h, or that quantity to the 4th power. F of x is x to the 4th over h. And then my problem now becomes, how do I expand the binomial x plus h to the 4th? Well, if you look in the box over here, remember if you have a plus b to the 4th, there will be 5 terms, count them, 1, 2, 3, 4, 5, and they begin with a to the 4th, and then some coefficient, a cubed b, and then goes a squared b squared, and then a b cubed, and then b fourth. So the powers of a go down by 1 each time, and the powers of b go up by 1 each time, and you'll notice that the powers always add to 4. The exponents add to 4. 3 plus 1 is 4, 2 plus 2 is 4, 1 and 3 is 4. And the coefficients, the missing numbers, can be easily found using Pascal's triangle. So let's reproduce that over on the side. We've got 1, 1, and 1. You will start with 1, add the 2 above, finish with a 1, start with a 1, add the 2 above, add the 2 above, finish with a 1, 1, add the 2 above, 4, 6, 4, and then finish with a 1, and so on. But actually, this is as far as we need to go. If I want the coefficients for the expansion beginning for a plus b to the 4th, I need to look at the line that begins 1, 4. So the first coefficient is 1, which we usually don't bother to write in, 4, then 6, then 4, and then there's a 1 at the end that we don't bother to write in. So we're going to use this result and apply it to x plus h to the 4th. So it is x to the 4th plus 4, and then x cubed h plus 6. X goes down to x squared, h goes up to h squared. Then there's a 4, x is now x to the 1, h goes up 1, so it's h cubed, and then we finish with an h to the 4th. So that's my expansion, and I'm subtracting that last term, minus x to the 4th, and it's all over h. Right, if we look, when we simplify the numerator, you will see that, the x to the 4ths add to 0, and then when I look at what's left in the numerator, and this is becoming really easy for you by now, there's a common factor of h. H occurs in each of the terms in the numerator. So we can factor out that h. We get 4x cubed plus 6x squared plus 4, whoops, I lie, 4x squared h plus 4x h squared plus h cubed. And that is all over h. Zoink, zoink, the h's cancel. And now I'm in a position to plug in h is 0. I get 4x cubed plus, oh, there's a 0 there. H is 0 plus 0. And so I get 4x cubed is going to be my answer. At this point, I hope maybe you have begun to spot a pattern. And maybe even you could go, I see the pattern. I could differentiate x to the 8th and tell you what that is. If you don't see the pattern straight away, let's go up and write down the results that I've got, starting with problem 2. With problem 2, let's go in and do that. What do we see? If I differentiate x with respect to x, I get 1. Okay, let's look at the next problem. That says if I differentiate x squared, I get 2x. All right, problem 4, which was a starburst result. If I differentiate x cubed, I get 3x squared. Okay, and then in problem 5, if I differentiate x to the 4th, I get 4x cubed. So, here's a question for you. What do you think you would get if you differentiate x to the 8th? Let's see if you are right. Okay? What the answer to that one is, if I differentiate, this is problem 6. If I differentiate x to the 8th, and you said 8x to the 7th, you are right. Okay, and this result is in fact known as the power rule. And right now we are actually only asserting the truth of the power rule for when x is a positive integer, because all our examples so far from problem 2 on down have been positive integers. And what the power rule says is that if you have x to the n and you differentiate it, the n comes down in front and you subtract 1 from n, from the exponent. So I'm just writing down the power rule twice. It's just using the two different notations. Okay. So this is a useful, very useful rule indeed. Now let's do a slightly more complicated example. Let's do problem 7. What do we do if we don't just have x to the 4th, but 11x to the 4th? What on earth are we going to do with that? And so the way we do that is actually very interesting. It's a little different. F prime of x is equal to, let's go back to our wonderful basic limit definition, f of x plus h minus f of x all over h. And let's see what we're going to get. For this particular function, it gives 11 times the input. So when the input is x plus h, we're going to get 11 times, the input to the 4th power. I don't think I said that last time. Minus f of x is 11x to the 4th. And it's all over h. Okay? Now, instead of expanding x plus h to the 4th like I did in the previous example, I'm going to resort to a little bit of algebraic cunning. And I'm going to say, look at that numerator. I have got a common factor in that numerator, and the common factor is 11. So let me factor that out, and I'm left with x plus h to the 4th minus x to the 4th. And it's all over h. Now, I'm going to use the techniques we met when we were doing limits. I'm going to take that one big fraction that I want to take the limit of, and I'm going to write it as the product of two things. The first fraction is 11 over 1, and the second fraction is simply going to be my x plus h to the, x plus h to the fourth minus x to the fourth over h. Okay, check it out. When I multiply out the numerators, I get what I had. 1 times h gives me a denominator of h. Now I'm going to use my laws of limits. The limit of a product is the product of the separate limits. So I've got the limit of 11 times the limit of my fraction and the limit of 11 we all know is 11. Limit of a constant is a constant. And have a good look at what we have for our second limit. If we scoot back to the previous problem, here it is. It's exactly the same as what we had. That expression, the limit as h goes to 0 of x plus h to the fourth minus x to the fourth all over h, turns out to be the derivative of x to the fourth. So let's write that down. Okay, this is the derivative of my x to the fourth, and we know that that is 11 times 4x cubed. So my final answer would be 44x cubed. But actually, it is not the final answer that is most interesting here. It is, in fact, let's see, this step. And look what we did. Look, we have, my original function was 11x to the fourth, and what was the derivative of it? 11 times the derivative of x to the fourth. So this is what is the important thing to take away. If I had, let's come up with something else. If I had f of x is equal to, I don't know, 31 x to the fourth, then the derivative of that is going to be 31 times the derivative of x to the fourth. Or to take yet another example, if I started off with, oh goodness me, 15, say negative 15, x to the seventh, then the derivative of that is going to be negative 15, and then whatever the derivative of x to the seventh is, and of course, using the power rule, you would know that is 7x to the sixth. Okay, but it's really this underlying principle that is most important here, because it is known as the constant multiple rule. And it says here, if u of x is a differentiable function of x, so you can actually take the derivative of it, and c is a constant, so I have a constant times some function, then what the constant multiple rule says is, oh, just take that constant, take it outside, and then simply take the derivative of the function u. So let's apply that principle. All right, we have got problem 8. Given f of x is 1/5 x to the 7th, what is the derivative of it? That's f prime. Well, let's have a little look. We have got 1/5. That's my constant. Oh, So if I want the derivative of this, I just simply take the constant out and I differentiate my x to the 7th, and that's going to be 1/5 times, and the derivative of x to the 7th, we use the power rule, 7x to the 6th. So I would get 7/5 x to the 6th. Okay? We're going to combine this constant multiple rule with two more rules. And these are the sum and difference rule, and they're really pretty straightforward. Given u of x and v of x are differentiable functions of x. So I've got, in this case, the sum of two functions. The derivative of the sum is simply the sum of the separate derivatives. And if I have the derivative of a difference, well, I just take the difference of the separate derivatives. That's all this is saying. So let's apply that to problem 9. Okay. I've got the sum of two functions here for problem 9. There is a strategic tip that I recommend when you have something like that, and this is to rewrite it. We can rewrite that sum as, instead of x to the 4th divided by 2, that's the same as 1/2 x to the 4th. I want to make it a multiple. I want to multiply by something if I want to use a constant multiple rule. And then this is going to be 1/3 x to the 9. Now we're in good shape. Shall I give you a few seconds to write down what you think the answer is? Okay, let's see. 1/2. Just keep that constant multiple there. Multiply by the derivative of x to the 4th. It's going to be 4x cubed. And then I have a sum of two things, so it's, when I differentiate, it's simply the sum of the separate derivatives. So I found the first derivative. Then I want to add that to the second derivative. So we're going to go that way. And I'm now going to differentiate 1/3 x to the 9th, okay? Constant multiple remains unchanged, and then all I do is differentiate your x to the 9th, which gives me 9x to the 8th. And then I do a little bit of tidying up, and I get a final answer. Okay, so to recap, what we had was the sum of two functions, so I just find the separate derivatives and add them. And then when I look at each one, they can be written as a multiplying quantity, 1/2 times x to the 4th, and then 1/3 x to the 9th, and I can use my constant multiple rule. So there's a nice problem for problem 10. I'm given, oh, I've got a whole mix here of difference and a sum and another sum. This is a mixture of sums and differences. I'm just going to say the derivative of this is simply going to be the sum and differences of the separate derivatives. So I just simply differentiate each of these separately. Okay, so f prime of x, okay, is going to be given by, oh, I'm multiplying by 10, constant multiple. Then I'm going to multiply that by the derivative of x cubed, which you know, and then minus, just because we've got a difference. And when I differentiate a difference, it's the difference of the separate derivatives. Okay, I'm multiplying by 6, constant multiple. And then it's going to be 2x, using the power rule. It's 2x to the 1, isn't it? It also is one of your starburst results, but see how it actually is following the power rule. Plus 5. And the derivative of x we found on the other page is just 1. And then lastly, the derivative of a constant, again, that was the very first result that came with problem 1. The derivative of a constant, remember, that represents a horizontal line, and the slope of a horizontal line is 0. So we would then tidy all this up and we get 30x squared minus 12x, oops, not good, minus 12x plus 5, and we are done. These are easy peasy, they are fun. B is our old friend, a tangent line. Remember, if you want a tangent line, you need a point and you need the slope. So to get our point, we know the x coordinate is 0. How do I find the matching y coordinate? Well, I need to go back to the original function, right? And I've got to plug in x is 0, right? So what is f of 0? It's going to be 0 minus 0 plus 0 plus 13, right? So it's going to be just 13. Okay, that's f of 0. So I've got my point. Now I need my slope. My slope at 5 is simply f prime at 5. This is my slope. Okay, so let's plug that into the what I got for the slope. There it is. All right, so that's going to be 30 times, oh, I'm sorry, it's not at 5. What on earth am I saying? Forget that. We're finding it, a senior moment here. It is f prime at 0. I want the slope of the tangent line at x equals 0. Sorry about that. So, but I'm going to use the rule for the slope function. And so f prime at 0 is going to be 30 times 0 squared minus 12 times 0 plus 5. That's where I was thinking ahead. That's where the 5 is coming from. So the slope is 5. All right. Now we're ready to write down the tangent line. The tangent line is going to simply be y minus my 13 equals 5 times x minus 0. Okay. And then we're going to finish up with one pretty straightforward question on the next page. It's really pretty easy. Find where there are horizontal tangents to the curve, and you have an expression for the curve without using your calculator. All right? So horizontal tangents means the slope, the tangent line must be horizontal, so where the slope equals 0. That's what I need to find. Okay, so let's start. I have y written down. Let's use as many different notations we can to get you used to the notations for the derivative. Y prime is going to be, we know this, or if we've forgotten, we can use the power rule. The 4 comes down in front, subtract 1 from the exponent. Now I have a constant multiplier, so that 4/3, I don't do anything with it. I leave it just where it was and just differentiate my x cubed. And then again, you can use either the starburst or you can use the power rule now if that's easier. So that's going to be times 3x squared minus 12, another constant multiple. And then again, x squared, you can use your starburst or you can use your power rule. The 2 comes in front, subtract 1 from the exponent, you get 1. And the derivative of a constant is 0. All right? Because you're talking about the slope of y equals of 7, right? If you want to differentiate that constant 7. That's y prime. And the question is, where is that slope equal to 0? So I have a formula for the slope function. All I need to do is to put it equal to 0. So 4x cubed plus, and when I simplify that, I get 4x squared minus 24x. That is my slope function, and I'm going to set it equal to 0. This is a cubic equation, but actually it's not nearly as bad as it looks. Let's factor out the common factor of 4x. I get x squared plus x minus 6 equals 0. And that factors very nicely. And I get the solutions. 4 is clearly not 0, but x could be 0. X could be -3, or x could be 2. And let's go back, make sure we answer the question. The question says, find where. It doesn't actually specifically ask me for points. If it had asked me for points, I would need a pair of coordinates, an x and a matching y. So mercifully, that's not what's needed here. The x coordinates will do just fine. And so this is where my horizontal tangents are at these points. And we are done. That is it. Let me